Okay, all right, we're live, and I am going to discuss today about product column density changes when you're pumping a product, when you're using a pumped explosive product. It was hit up a couple of times about talking about this subject or providing information about it, and I thought it best to show you a spreadsheet that I use. And there are plenty of spreadsheets around out there that may provide the same information, but I thought rather than just give a spreadsheet out that has the answer in, I thought I might talk about how to make the spreadsheet at least and what we're looking at. All right, so initially we need to consider a few concepts with explosive products, and one of those is that they all have a limiting density. So we need this value. We need to know this value, and this changes based on the product manufacturer. So if you're talking about an emulsion product like a traditional, what you see, a very common product, what you see around the world today, emulsion or emulsified explosive products, and they are fuel and waxes mixed with water and then emulsified, and then you add those to ammonium nitrate and fuel oil or an ANFO mix, and that creates a blended product. Now, what we lose when we blend a product is we lose sensitivity. So we either need a large volume of it and a nice big hit of energy to get it to detonate, or we add sensitivity to it, and we add sensitivity to the product by adding bubbles of air. Now, with emulsions, they use chemical gassing generally, but you can use mechanical aeration or a mechanical encapsulation of air. So that's whipping it in, like turning it into like a meringue, so to speak. So excuse me let me just take a drink of water here. Tickle in the throat. Okay. Moving on, and then we need to know what our starting density is. So we've got once we've gassed that product out of the processing unit, we need to know about what our column cap density will be, or our cup density will be at the atmospheres that we're working at. And so, in here we've written 1.1, and for limiting density I put 1.35. That seems reasonable for an emulsion, but if you're talking about a water gel or something like that, this could be up to 1.54, which changes the matrix. So you need to know something about your product. This doesn't just, you can't just use any table. You need to know something from the manufacturer, and that is, how dense can this product be when you give it to me? How dense can it be without any air? And that's what the limiting density is. Okay, because that's as dense as I've written over here. Limiting density is the most the liquid can be compressed, and this is generally the mass of the components without any gas. Obviously, structure plays a bit of part in that. And you can't get away from that. This wire is annoying me. Anyway, moving on. Then I've got this little button here, or this little option here, about changing the interval length. And that's just because in the chart I show you we can do 1, but sometimes, like if you're using this calculator to match a person's product or a competitor's product to yours and find out what difference, because a lot of these density charts are also compiled through experience with the product, or different thermodynamic codes and those sorts of things, and different methods of finding it. So this is just a generic method that I'm presenting here. And then I've got a manual adjustment. So we're just talking about this only because perhaps you want to simulate what density the product would be if you just left water on top. So there's a hydrostatic pressure on that. So you're going to add a certain amount of like in this example here, I've said 10 meters of water would be in 1 additional atmosphere. So if you were pumping products, not that you could, but let's say in a world where anything's possible, you're using commercial mining products to put 10 to blow up the bottom of the ocean floor or something like that at 10 meters of water depth above you. Well, there's a hydrostatic pressure on there that's pushing down on that product already, and you understand that by if you take a kid's basketball or a basketball to the bottom of a swimming pool, it'll get squashier and softer, and that's because there is a lot of pressure from that environment, a lot of hydrostatic pressure, a lot of water pressure pushing on that object, and as you go deeper, the pressure increases. All right, I'm trying to get a few concepts across here, and some of which I don't all understand myself because this is an entire field of science sort of thing. So then we have our atmospheric pressure that we're starting at. So I'm going to put it at like 1, which is generally the sea level. But if you go up in altitude, your atmospheres will drop, and if you go obviously below the ocean, they'll get more. So as you can see in this little example here, I've said 1, but if you're doing this on the top of Mount Everest, well, this would be 0.3326, right? Well, which that would change completely the equation. Okay, and then so let's just put that at 1. Right, and then down here I've got a diameter. We need that diameter. Got to know that. Yep. And then we've got 1 atmosphere to pascals, or I've written here 1 atmosphere to pascals. But this essentially is what your atmospheres are up here, converted into pascals. So that should really just say atmospheres to pascals, right? And that number there is just found on any website, and I've got a few links over here in this spreadsheet where you can find a little bit more out about different sorts of things, about the ideal gas laws and those sorts of things, which these are based around, the whole P1V1 equals P2V2 is one of the crux of the equations in this spreadsheet. All right. Sorry. I can't believe how dry my voice is. So, we then also have a pascals to atmospheres conversion back. So this doesn't really need to be called constant, even though it is a constant value, but it just is that. And then we have just a bit of conditional formatting in Excel. So I've just said this is the number. Now, like we just set this limiting density of 1.54, which means that potentially our critical density here would be more likely somewhere around the 1.34 mark for a water gel, and if you're talking about a emulsion, then you're probably looking at this being anywhere between 1.32 and 1.38 probably. So let's just say 1.35 for our example, and down here we'll put our critical density, which means now critical density is when the product is not going to detonate, it's going to burn, right? So it might not even burn, it might just completely flop and die. So let's put this at 1.27, rightio, which is reasonable, right? What our critical density would be. Okay, so we need these values. We need a limiting density. We need to know what our cup density is. We need to do a table interval amount. We need to do a well, we don't need to do the manual adjustment. We can ignore that. We need to know what pressure we're going to start at. So let's say in this case we're doing atmospheric pressure, and then then we go in diameter, atmospheres to pascals conversion, and the pascals to atmospheres conversion, and then also critical density. But this one's just an information piece. And what this produces is right here. We've set this up. What this produces is this little chart down here, which says our length or depth of hole. So we're going to say this is length or depth of hole, and this is the this is the density at that depth. So so starting with a cup weight 0 meters, it's 1.1. At 1 meter down, it's 1.12. Right, so it's a bit denser. Right, and that's because 1 meter there's a slight increase in atmospheric pressure. And then, sorry, just a second, we had a little phone call there. Excuse me. I'll just message that person back quickly, call you later. There you go, getting distracted. And then we have a average density over the length of the hole, and this is just sort of like the grouping of those two together. This looks like it might have, and no, that's good. That's got it. So we're just taking this one, and on the second one, we're saying what the average is here between all of these. So we're adding up, and these will slowly get averaged out over the course of that. Now, why can't I see that? Is because it's a table, so it's doing it automatically. Interesting. Rightio, and then we show on this side the kilogram weight of each interval, and I've just shown that for a bit of interest's sake. So if you just had 1 meter of product at 20 meters deep, it would be 10.3 kilos, and at 2 at 9.2. So that's like a slice in the product column. Okay, and then we have the weight accumulative over here, and whether it's critical, and you can see at 24 meters it's gone critical. So this is the accumulative weight. So if you had a 24 meter product length of column, you would be looking at 248 kilos there, and it would be, you know, at a toe density of 127, near on critical, and its average density over the product column is the other one. Rightio. Okay. Making sense. I'm a little concerned my chart is broken at this point. This looks like it's just gone down here. It has. All right, this is what. So let's fix our average density up. So our average density is essentially, first one is the first value, but the second one is a average of these two values. So let's just see what's going on with my computer program here. So I want to say in here, this one equals this. Let me get this right. Yep, sum. So we're going to average it, actually. There you go. I'm messing it all up. So if you give me time to think about it, so this one is equal to this. That's correct. Density at depth, not a problem. And then this one here is equal to density at depth plus the average of those two. Or not that plus, so not that average. So we'll get rid of that density at depth business in a second here. We're just going to get rid of this density at depth. So I've broken my own spreadsheet in prior to making this. So let's just go average of those two. Yep, correct. And oh, just want to lock that first one in. Right, so where is it? There. Right, so we're just locking that there. I don't know if you can see that. So I've just, it's blue, so it's a little bit difficult to see, but essentially it says average in brackets, and then it says $D $14 colon D15, and I've left the D15 unlocked because I'm going to drag this down. It's going to go B all the way down. Okay, tick. So I'm going to take that value there and drag that down. I've got quite a few cells here. Alright, that doesn't seem to have done what I wanted, but it looks like it might have. And we will have a look. So we'll tick that. And here we can see here that it's $14. It's this entire group we're averaging, which is exactly what we wanted to do. Radio. I don't know why that was broken, but as you can see, there's a slight shift in density, and here we are. This is much better. So there you can see this has changed this amount, because this is what our average column is looking at, is this value over here. And looking at this length. All right, so is this, hopefully this is making sense. It was a little confusing there because I messed it up, but so this is pretty much how we can determine what our kilo amount is and our mass. And so what we have is these equations here. So just this one up the top, this one here, and then our average is pretty much critical to what we're looking at. So I'll just move that across. So this is depth at density based on the atmospheres of the pressure, or of the pressure. Yep. So that's just the equation there. So we're going to find the maximum density of the mix. So that's the critical density of the mix. And we need the density of at the surface, and the maximum density of the mix, again, is a bit of equation, and then we divide it all by the atmospheres that we're applying the pressure to. Rightio. And here we have we can add the manual adjustment, or we can just ignore that line there. And if we're not looking for the manual adjustment, we can just ignore it and get rid of it. And this equation still works. It just won't take into account the hydrostatic pressure that we apply. Okay, and then we have all the rest of this equation. Okay, so what we're trying to simulate with this equation is these scenarios where the product is getting denser at the toe, and it's adding density to that toe. Now that creates a much larger mass within a volume, and we're also trying to create this thing, or trying to simulate this thing. The only difference here is that stemming or crushed angular aggregates, like, they push out on the boreholes and they push slightly down on the product initially, but once they interlock, they're not applying pressure. But the depth is, the product is. And here we have hydrostatic or hydrostatic pressure on top of the column, and this is well, you can't take the bottom of a, well, I suppose you can actually. If you fill the cup with water and you turn it upside down, you hold like one of those magic tricks, and you take the beer coaster away from the water, it stays in the cup, only because it's stuck to the vessel. But in a blast hole, it's not stuck, so it's just falling down and always pushing pressure onto the product. Something to think about there. So this is the three sort of scenarios, and these are the equations that we use in here to make it up, and this is the chart. So let me just zoom out so we can see. I don't know if you'll see all this. We sort of I have a little chart, graph over here, just saying this is the critical amount. Over here, 1.27, and so at sort of like these are the depths, so you can see that they're not going to be critical. This is average, and this is in hole or at depth density. I think you'll find on my chart. Yep, average density point, radio. So the words are really small. Hopefully you can see them a little bit. But as we change this, so then we can do a little bit of a shift here, and 1.05, and hit enter, and now our chart's changed, and our total kilos over that mass has changed. And you can see here that it's completely different, because our critical density has now gone deeper. So as we use a lighter density, we have more room for that compression till we get to critical. And as you can see, before we were at 24 meters and it was critical. Now we're at 34 meters and it can be critical. So that's something to investigate and understand. Now, our critical density, because all these numbers work together, our critical density can be affected by our limiting density, right? So if we still had a 1.27 critical density, that was when the product failed, but it was actually 1.32 was our most dense the product could get. Well, what's our critical density now? It's shifted even further down to 54. So it's less room. There's less room between those two states to compress the product. So it's a build-up of force, an exponential force, and we can tell it's exponential because our results are curved. So eventually it gets to a point where you can never compress this product. You'll never be able to get the product, no matter how deep you go, to get to 1.32. You just won't do it because you can't squash all the air out, and that's essentially what we're doing. So we're like, if I was to look at the examples here, and we were to kind of try to insert something quickly. Like let's say I got a mass, and in that mass I'm going to place some air bubbles, right? And we'll make those white. So I've got some air bubbles in here, and sorry, just got to copy a few down there, right? So we've got some air bubbles in here. Now this has changed the density. So if we were to take all these air bubbles out of the mass, then we have a limiting density, right? So let's say that is 1.34, or 5, or something like that, right? 1.35. Can you see that? It's very small. So let's make that bigger. Right, so we have a 135 limiting density. Now when we add some bubbles, and we're sitting on the bench of the shot, we get our truck and we add some bubbles, and we change that density down to, and now what should we change it down? Oops, sorry, my bad. We change that density down to, like, we regas it to 1.10, right? Seems reasonable. Or let's say 1.15. Okay, so when we compress that, we add air into that mix, then we add pressure to that. And so what are we doing with this pressure? We are changing the size. So I should have replicated that as well. So we had our mass without... We have our mass without, I should have done that. So this is our mass without air, and we'll put in and then we add air to it. Right, so we've got our mass without air here in the first stage. And then we've got our mass with air in it in this little bit. Now what that's done is that what I'm trying to show there by an example is that when we add the air bubbles, that fills a certain part of that vessel and it makes the volume larger if we keep the mass the same, right? And this is just simply this equation, right? Sorry, not this equation. It's simply this density mass equation here. Essentially, if we have a mass of 10 kilos and a volume of 8 kilos, then our density is that. So if we add air to our density, so let's say over here we have a volume, right? And we say we have 1.34. That's our critical density. So our mass is 10 kilos and our volume is only 7.4 cubic meters. Okay. So what we do is we are going to add air to it, and so what we do is we're reducing our mass. We're reducing this to 1.15. Our density, and you can see here our volume increases. Our volume increases, and that's what I'm trying to show here. Just a second, 2 seconds. Okay, sorry about that. I was just seeing how my dog was going. Just having a little puppy dream. Okay, all right. So that's essentially what we're talking about there. Is this? We're adding air or gas in the form of chemical gassing. We're generally including nitrogen, non-flammable gas. And we're adding that to the product, and when we then apply pressure to it, we reduce this volume. So let's make another copy of that and paste that in there. We reduce the volume, and some of these concepts everyone will know about anyway, so apologies if you already know this stuff and it sounds like I'm telling you stuff you already know, because that's not the intent. The intent is to go on a learning sort of journey. And so so we have our air bubbles in this green section, right? And when we apply, so we had our air bubbles in the blue section, the dark blue section, let's say, this was dark blue, and then as we apply pressure, we are now, reducing the size of these bubbles, because that's what's changing, right? Is the size of these bubbles. Okay, and that changes the density, right? So it changes the density, so then we end up with like a 1.2. So that's what's happening, right? We are squashing the air bubbles. Now it comes to a point. What is critical density? It comes to a point that this critical density occurs, and that critical density is from that crushing. So as the product squashes these air bubbles, they get to a point where they're too small. So 1.2 for the moment, I'm going to say. And when those bubbles are too small, the product will fail. So if there's not enough bubbles, or they're not the right size, and they're not the right distribution, and they're not a whole bunch of physical properties, then this sensitivity of the product disappears. Now, what about ANFO and heavies and all those sorts of things? Well, ANFO and heavy products, they still compress a little bit, but they're more of a structural compression. And that's just because, with any weight, everything gets crushed or broken or squashed. And with ANFO or heavies, the gap of air is not via gas. The sensitivity gap is between the prill balls, or internally into the porous prill, into the crystalline structure of the prill. So it's got all these structures inside it that keep it that certain shape and density, because ammonium nitrate's like and you'll have to check me on this, ammonium nitrate's density without any air is like 1.73, I think, but it could be 135, I think, 1.35. I believe AN's density is that. So I would check that out, because don't quote me on that one. It's off the top remembering, and I have a feeling that I'm wrong. So please check that out. Go and look it up. But when that structure has been created created from doing it created in a factory, the ammonium nitrates added has air in it. So porous prill has that air in it. So it's already got air encapsulated inside the prill ball. All right. Now, I did say we were going to do this chart. So what is the equations? They're pretty simple over here. Like those equations were pretty simple. Sorry, I'm just looking in here. And these are the equations that we're going to be using. Let me dial that down so you can see it. Hopefully you can see it all now. All right, so these are the values we're going to be using, and these are the things we're looking at. All right, what are we looking for time? Half an hour. Okay, so let me do a very basic tutorial on how to build this. So let's add in a blank sheet, and we'll call this video build. So this is for people if they want to move along and build with it, right? And I'm just going to do a couple of simple things. Rightio. So first of all, our chart, we needed these aspects of it. So let's just put in all these things: limiting density, column cap, all these things here, right? So let me just grab those for posterity's sake. Copy, and we'll walk through building it again as a reference. We'll paste the special just as formulas, right? So we need a limiting density. So this is the most dense the product can be. So we need that value, right? And we're going to do, I think what we'll do here is we'll build, we'll just build it the way I had it. So there. So this is on the fly. I haven't rehearsed this bit, so you'll have to forgive me if I get it wrong. I've got a couple of things wrong today, so it's pretty exciting to be wrong. Not really. Then we need a column cap density or a cup density. This can be anything you like. Obviously, it's something you might use on your site regularly. So let's say our cup density. We'll call this a cup density. So our limiting density is going to be something you need to ask the manufacturer for. You have to ask, let's say you have a Dyno Nobel contract for you. Then you'll have to ask them what their limiting density they use is. You can look at their tables, I suppose, or you can ask one of their representatives and say, what's the limiting density of your product? All right, and so generally we're going to say it comes to the yard. We're just going to guess it. I mean, it says it comes to the yard at 1.32. Yeah, when we take a cup of the emulsion that's been delivered to the yard, it's 1.32 grams per ton, or grams per cubic centimetre. Sorry. And then we say, well, we're going to always pump at our quarry, mine, operation, whatever. We're going to be pumping 1.05. Always. Right? We very rarely change that at this site, I'm going to say. Right. And then we're going to move on and we'll say, well, we can do an interval amount or we can ignore that. Let's ignore the interval amount. Right? So we'll ignore the interval amount and we'll just say that we don't care if the interval amount is 1, or we can type it in. Let's just type it in, interval. One. So every meter, this is in meters, this is 1 meter. Right. So pretty easy. I'm going through this very simply, so forgive me if you already have done it, but essentially we're just going to write in all these things. Then we need the manual adjustment. Well, I'm going to ignore manual adjustment, not even going to look at it. So then we're going to move on to the atmosphere. I very rarely use the manual adjustment. This is still ideal gases. So this is still ideal gases. So it's not truly true in the real world. There is some grey in this. Yeah, some unknowns. So the atmosphere, we're just going to say one atmosphere at sea level. Let's say maybe we're a bit higher and it's 0.9 of an atmosphere. Honestly, atmospheres don't make too much difference to the equation. I mean, not unless they're significant. And then we need a diameter, right? Diameter. We definitely need a diameter because that's the volume. So we're going to put in 89 mils there. And then we need our constants, our conversion constants, right? We need to know what an atmosphere is in pascals, and that's pretty easy. That you can find that on any science website or even Wikipedia if you're desperate. Rightio, and that is ATM to pascals, right? And this is pascals to ATM. Okay. And this is an exponential number, so let's look at what that looks like. I'll just zoom that out so you can see this. This is quite a large amount, so let's just take off scientific, go to number, and crunch across here. So we're looking at these values here. Quite a few significant decimal places. I think that's it. Oh no, it keeps going. There you go, ends here. So it's quite a long number, right? But it's 1 divided by the Pascal's constant. Pretty easy. Wow. So it's 1 divided by, well, let's put an equal sign. So this is now 1 divided by 101,325. And so that's going to give us our equation, right? Which is exactly what we had before. Pretty easy. Yeah, I say that a lot. Pretty easy. All right, so these are the units next to them, right? We got grams per cubic centimeter, but it could be kilograms per liter, kg per liter. They're the same as GCC. This is a kg/L, so don't get hung up on the density stuff as long as they're units for units, equivalent units, should I say. Interval amount will be in meters. Atmosphere will be in atmospheres. Diameter is going to be in millimeters, but you can do it in meters. You just have to add the division multiplication sort of function into the equation. So because this equation doesn't have it, and as a drill and blaster we kind of talk in millimeters, probably more than meters, so I'm going to do it like that, even though meters is a scientific unit. And then this is pascals, right? Because it's going atmospheres to pascals, and this is atmospheres. Okay. Alright, I think pascals to atmospheres. Yeah, well, it doesn't really matter. So let's not get confused with those two constants. It doesn't really matter too much. These are conversions, so they might just be numbers. Rightio. So at this point now, we are going to set up our first table, and that'll be our depth or length, right? And this is just going to be 1, and we're going to grab that 1 and drag it down. Let's just grab a few. I don't know where that's going to end up, so drag 1 and we'll do fill series. All right, so 1 down to 10. There you go, pretty good. pretty lucky. So we can do it that way. Or, since we've got our interval amount, we can click that and go equals let's say 1, right? Tick. Okay, and then the next value, instead of that being, that's equal to 1 up there, right? They're linked. So our next value would be equals to our previous value plus 1, okay, what our interval is. Okay, and we tick that, and then we just drag that down, right? If we get it right. Why didn't it do that? Unbelievable. So that's there, H7J, yep. Okay, tick, should have just, gone down. That's why, because of this. I didn't lock it. How silly of me. So we're going to go H7, which is the blue cell, and we're going to lock the red cell. And we lock that by pushing the F4 button. If you're not an Excel guru, then this is learning Excel for you as well. So we lock that up, and there it is. And now we can drag down. So we're always referencing the interval amount. Here you go. So now got 1 down to 10. That's our thing. So let's try that out. Like if we change this to 0.5. Well, there it is. Okay, pretty easy. Or we change this to 0.7. Rightio. So that changes because it's linked now. Okay. I forgot 0 because 0 is our base start. So let's just put that at 1. And we'll move our length up. And we'll move this. We'll change this to 0. And instead of that being 0, that being 1, and that being this, we will drag that up to there, and that is the same, right? So now we have 0.5. Let's try that. Yep, so that works well. 1. Okay, that's exactly what we want. Now we're going across, and our next one is, what do we have? We're going to jeepers, got to reference this here, and we're going to use density at depth. Well, you can have density at depth, right? And then we want pressure, average, so there we go. This one probably is more important for your usable values, which is kilograms weight length. Okay, so let's go back to our video build, and we're going to say, already my brain forgot it. So density at depth. We're going to use the density. Jeepers density. This is going to be the density at the bottom of that segment. So over, at that. It can be wherever really. So it's the density of that bit. Alright, so this is the first equation that we had in the previous one, right? Now let's just go over here. This is density at depth. So we've got the maximum density of the mix and the density at the surface. And so let's just, let's copy this one because it's a bit easy to read this one, right? So this is our density at depth. I'm just going to copy that in there. Copy, and we're going to put that into here. Paste. All right. And now we're going to change it to what we're looking for. So we're just going to highlight these words, limiting density. Oh, my, I must admit the Mac is no good for Excel. So I've got this limiting density here, and I'm going to select this one. So I'm going to replace it with that one, right? Well, that didn't work very well because I'm not in a equation, am I? So let's push an equal sign in front of it. Now that puts us in the equation sort of building thing. And now we can just double click and click. Now we can see this thing hovering, and we can click on this. This is what it's going to be, limiting density. Now, what do we need to do with limiting density? We need to lock it. So whilst we're there, we hit F4 and we lock it to limiting density, because there is only one. There's the one limiting density. And then we go to cup density, and we're going to do the same. Click on that one, and we're going to lock that one by pushing F4. Right, and so we're just going to follow this along. Limiting density again, select that, and F4. Right, and atmospheres is what's going to change. And atmospheres is probably going to be this next column over here. We're going to put this in this next column. So let's excuse me, click on this one. And this will not be locked. This will be growing as we go down. Now, obviously, this is going to be an error because it's going to divide by 0. So let's just tick that anyway, and definitely going to be an error. And this was going to be atmospheres. Right. Go. There you go. I can't spell. Right, so atmospheres. Okay, so our first atmosphere is going to be, well, this value up here, right? Because this is our starting atmosphere that we talked about, and this is 0 depth. So definitely this one is going to be this. So let's just plug this number in at the moment, just to show you by hitting the equal sign and then selecting K3, and we tick, right? So now we get this this value here. It's a little bit odd because it's not right. Well, it's actually our cup density, so that's not going to really work. Can't really go much less than 1, can we? And that's what it should be. So that's working. So obviously our cup density is based on it being at 1 atmosphere. So we would have to factor that in, because if we were above, it would be different. Okay, all right. Okay, so let's just focus that this is starting atmosphere of 1. That's our atmosphere at sea level. Moving on, so we have 1 atmosphere in there. However, that just generates this value. So now, if we were to go and drag this down to here and let the equation work it all out, we'd have a division. And so if we were to just drag this down here, but instead we would do, we would lock that. So if we get that there and we lock that, just for this is an experiment, we don't need to do this bit. We're going to always get, doesn't matter, because we're always trying to find out what our density, so we need our density to shift based on how much pressure we apply, because that's the equation, right? We're changing the density via the pressure. So we go back to our equations, and we've got terrible thing. We've got our pressure here, and we look at this pressure equation, which is here, right? And that is this one here, pressure column. Yeah. So I'm going to copy that one there and go into here, and we're going to paste that in there. Rightio. Oh, what an ugly thing. Undo. That one messed it all up. So let's just paste the value. Right. Now it is broken. Right. So if we look at this value of atmospheres, and we want to turn this into an equation, go to the first value here in front of the first value and push an equal sign, right? We make it an equation. Right. Now we are looking for this manual adjuster, and we got rid of that, so we're just going to delete that out. I don't want to know about the manual adjuster. I don't want to know about it. Well, let's just double click and delete. So I don't even want to know about the manual adjuster because we left it out. So that's as simple, you're just adding manual adjuster on the front. So here we go to cup density, and we're looking for the cup density, right? So here, that's that 105 number. Good. And we need to lock that, obviously, F4. And then we're looking for this kilograms meters squared as pascals, which is this value over here. So let's highlight that. God, it's very difficult to do this on a Mac. I'm just going to do it like that. There. So we're going to replace 1 kilogram / meters squared. I know it says 2, but it's a square. It's a lift one. And we're going to replace it with this value over here. No, we're not. Sorry, my bad. We need another value. And that needs to be in this column here. Okay, and I'm going to add that in. I cannot believe, but first of all, I'm going to lock it because it was wrong. And in here we're gonna put this value in, that value. So let's just tick that. It's going to be wrong, but this value is 9.8065. I think. Let's just go back over here. 6532. Sorry, 9860665. This is a pretty bad video. 0665. Yeah, I don't know why that's got a space in it. There you go. Right here. Got this value in here, and this is the 1 kg / M2, whatever. We'll just put it like that at the moment. I think it's PA. Right here. Okay, this is our value here that we want. So we want that one in there. So in here we were at this point. That was that value. That red value is 0.3, and then we want our depth, which is over this side, and then we're leaving it at 1,000, and we don't change this 1,000, and this atmospheres to pascals we need. So that was atmospheres to pascals. This is that 101.325 constant, and we will lock that. Very good. The depth doesn't get locked because it's going to follow this cell's going to follow all the way down. And then we're going to go to pascals to atmospheres, and then we're going to go back to the pascals to atmospheres constant, and we're going to lock that one with F4. Right, so now that just is locking a cell $N $3. Okay, and now we can see that's 1 atmosphere. We're going to drag that down. We get these values here that populate out. Now, terribly long-winded, so let's just grab all these. We'll grab these here. Well, let's grab these ones here, and we will make them numbers, and we will give them only 2 decimal places. That's good value. Brilliant. So you can see here at 10, it's double atmospheres, right? So it's what the ocean does. So this is now their density at depth, right? So then we want the average density, right? And we did this before because I'd broken my spreadsheet. Average. Let's just average density for the sake of it. I've broken my spreadsheet before, but now we're doing this. So this is the average density. So we're going to do this, and remember what we did last time. It was it's pretty small here. Maybe I'll make it bigger. All right. And this is the most exciting video you can ever watch, is someone in the corner talking about a spreadsheet. So we can now go with our average density and find out the average density. Now we are going to go equals our first density is our first one. And then our second density here that's going to be averaged is going to be the average of these two, right? So it's going to be equals 105 and 107, but up the top there we're going to type in here, or in this cell we're going to type in average. All right, and put a bracket at the end of it. Okay, so we got our average there. So that is averaging 2 cells. But what we want to do is if we drag that down, obviously if we drag that down here, we're only averaging the next two cells over here. We're missing this third one. Okay, so what we want to do here is we want to lock our first cell. So our I6. Alright, so we just push that and go F4. And you can see here is $I, $6. Awesome. Alright. And now we're going to drag that down. Alright, pretty easy. And now we can see that we're locking. So if we go to that last cell, we can see that we're averaging all the previous cells over this length. We're all good there. We can see that. So now we've got a... Now from this equation, we can calculate two things, right? We can calculate the density at, or we can calculate the mass at toe, which is what I was going to say, or at the bottom, the bottom mass of it, or we can calculate the product column average, or how much is each product column going to be. Pretty okay. So our next one is, well, we can add in this one, like the kilogram weight at each interval, or we can add in the kilogram weight of length of the entire length of that column. Up to you how you want to do it. I'm not going to do this one, kilogram weight at interval, because it holds very little information for me, only to tell me that as I go deeper I'm putting more explosives in the bottom of the hole. And if you can get these to detonate, then you're getting more energy at the bottom of the hole until they go critical. So let's just use this one, which is the kilogram weight of length. Right now, this is one of those old tried and tested calculations, which is just the the diameter of the hole times the density times the length, all that sort of stuff, which is pi r squared, all that. So let's have a little crack at this equation over there, and it's essentially we're looking at this average density value and the length, and then we're looking at the millimeters, so we need to know the diameter, and we're that's pretty much it. It's pretty easy calculation. So let's close that one. We'll go to the video build, and now we're going to type in here what it is, right? So we're going to type in, this is kilograms. Oh, kilograms, we'll just say accumulative. Are you serious? That's why I spelled it wrong. Rightio, here we are. So here we are at this point. So the first equation is to work out the volume of the blast hole. Everyone knows, every good engineer knows this one, which is pi r squared. So this is pi times the diameter halved. So we'll put a bracket there. Diameter divided by 2. Close the diameter off. Maybe we'll wrap that in a set of braces and put in a, not a P, but a little hat and a 2, pi r squared 2. Now you can do it that way, which we all love, or we can do it a much more complex way by doing a power function over that. But this hat 2 means, this little top hat means an indice, right? So the other way is to go power, right? So some people like to use powers. So let's use powers here. So we'll type in here power, and that's that value there, and we'll delete that. There you go, power. That is delete that. So now we're, instead of doing that, well, let's see what this looks like. Oh, done something wrong there. Tick. What? You've entered too few arguments. Sorry. Oh, that's right. Comma 2. What a silly Billy. So here we have this equation. We're going to spread this equation out so you can see what is written there. Pi times power L2, and then it's wrapped with a bracket there. Yeah. So pi r squared, that's going to get us one value. Then we're going to multiply it by the length, which is 0. And we're going to multiply it by the density, the average density, because we're going to be calculating the cumulative amount over the length of the column. So we want it to, the amount to be worked out on the last average density at that length. So we're going to do the average density. Click there. Pretty much, yeah. And we just need to lock this diameter in, which is the, radius, so well, it's the diameter, but we divided by 2, so it's the radius. We're going to lock that so that doesn't shift. Rightio, pretty much. So we've got length, so we've got volume, and we've got density, so we've got mass. Right, 0. Well, that's exactly what we were expecting. All right, now there's something a problem here, and that's because we didn't divide by 1,000, right? So we need to divide by 1,000 to get our proper kilograms. So that can go either before the density and the length or after everything. So let's just do that. And we'll divide by 1,000 to bring it back down. Now you could divide this here value by 1,000. Do it there earlier on. So that's divided by 1,000, drag it down. Alright, so there we have our values, or our cumulative amount. Do number, that size. Alright, and we should just go and check that all our equations are right. Yeah, so this is our mass. So let's put in the other end here. It's pretty easy when someone explains it to you. So we had, what did we have? 105. 105. One atmosphere, yeah, and we had a 89 mil hole. Right, yep. Don't worry about the critical, we haven't got to that yet. And we had our values are here. So let's just grab these values over here to head down to 10. We'll just copy those. Go over to video build, and over here we're going to paste them as paste special as. I'm sorry, you can't see that because it's off the screen. So I'm going to paste special as values. Yeah. And we're going to format them. Oh. Why has it done that? Custom, silly thing, number. So yeah, it's exactly the same. So our equation is working because these are just numbers up here. There's no equation in there. That's just the values of what we did from the other chart. So that is it, essentially. Now, what do we have missing in here? We had a critical density. So let's put in here, we want a critical density. So let's put over here our critical density. What do we got? We're going to put in 1.27 as an example. Again, kg/L is our units. 127, and we're not going to get there anytime soon unless we change this. So let's say our critical density on this product is like I don't know, pick 116, right? So it's a 1.16. Now it's important to note that diameter. It's important to note that diameter. The critical density is what the critical density is, but there are certain physical limitations to chemical explosives. One of those limitations is that as the borehole shrinks in size, it's more effort for the explosives to propagate, and so they run out quicker. So you know, they don't run out, but they slow down faster. The explosion slows down. So they start off being overramped by the booster. They're sped up, only 3 diameters, so 64 mil hole or a 76 mil hole or 89 mil hole. Let's say we're only 89 mils. It's like this much, yeah? Something like that. So after this much room, like after a foot of space, the product should be burning under its own steam at steady state. This is why it's very important to get your booster in good product and have no air bubbles and gaps now. So if you're in 64 mil hole, let's say you're in a 64 mil hole, which is really narrow. It's only like, this is about this round, right? About this round, this cup round, right? So if you had a gap this far apart of, you know, from my hand to the bottom of the bottle, if you had a gap there, how much do you think that the explosion energy down here is going to set this next bit off? You can't be guaranteed. So you need continuous intimacy with this product, or otherwise with any product. So it's important to know that your VOD and the propagation rates and all those sorts of things are affected by how the product is loaded into the hole, how it's loaded. So if it's not loaded very well, then it's not going to detonate very well, and therefore all the things that the client or the things that the salespeople will tell you about explosives, lost, gone, won't help you. Okay, so moving on. Anyway, I was talking about this critical density. I'm just going to give this critical density a red text. Okay, and then in this group here, and just for posterity's sake, I'm going to change every color in here with a conditional format. So pretty easy in this. Hopefully I get it right. I selected all the holes, and I just go in here and I'm going to new rule. And I'm just going to change this new rule to a classic for mine. On this is on Mac, so I apologize for those people on Windows. I'm just going to click red text, right? So red text. Okay, and then I'm going to change this to a formula. Or, yeah, I'm going to change this to a formula. Yeah, I think so. And so now I'm going to say in this formula, I want all these cells in here that have the value of 116 or greater to be red. So I'm going to say if let's say it's if I6, I'm going to change that from I6 to I6, take out the dollars sign. That way it's going to lock to the I column, but it's going to look at all the cells down. Sometimes this doesn't work. If I6 is greater than this value, which is locked G dollars, sorry, dollars G dollars 3, then I want to see red text in all these cells. I think that's all I need. Let's say, should we do greater than or equal to, or no, greater than, okay, red text. Or we can do a custom one. Let's customize that format. Make sure it's a nice bright red. Automatic color, and we'll do a bright red. And should we do a border? And we'll do a line color of red. So we'll give it a red border. And we'll bang that there, bang that there, and bang that there. Okay. I like that. Maybe we can do a font and do it as bold and bold italic. There you go, bold italic. That's always good. Okay. All right. So I'm going to hope that this all works. I click OK. And no, fail. Look at that, fail. And why would it have failed? Let's have a look. Because sometimes conditional formatting doesn't understand exactly what you want, and so it goes and puts in commas around it. Oh, sorry, yeah, so it's put a little comma around it right there. So we'll delete that and take out these quotation marks. Oh my god, I'm not having a very good time with that. My goodness, should I have said. So there you go, we've locked it there. Is it? Yeah, okay. Thinks it's a formula you typed. Alright, let's see. Just delete that again. I think this is right. Oh, like a nincompoop. I don't need this in a conditional cell. Sorry, I just need to look at these cells. I just need this equation, which is, look at this. It's already doing a conditional, and a conditional means an if. So if it suits a certain, this formula, it's going to do this thing. So I didn't need to say if. How silly. Click OK. Let's hope that it works. I'm going to edit that rule again and just get rid of these. Why does it do this? Tick OK. Okay. Right. Yay. There we are. We now have our critical density showing value here. So these are critical densities at the toe. This is what's important, not the average density. We don't care about the average density. We care about where our booster is. And if we put 10 meters of product in and our critical density is 1.16, then it's going to have a little bit of difficulty detonating. Wow, this is a long stream. I hope that this was useful. So you can slow and stop it down anywhere. I hope you could see it. So essentially our equations are depth is fine. You know, that's just, you can do whatever you like with that. But how about we just copy these quickly. Oh, cancel that. Now I'm going to put that there and paste it and then delete that, and so now the equation for this column is this. Yeah, for these are all the numbers, right? And this equation here will copy this equation out like that. Okay, that's that equation. Okay, pretty easy. Or let's put that there and click here, wrap text and middle. Let's see if that works when we squash it down a little. Yep, that works fine. Okay. All right, and then our next atmospheres value is this one here, right? Pretty easy there. So we're looking pretty good. We took the manual adjust off here, remember? Put that in there. And our next one here is atmospheres. Well, that's nothing. Oh, sorry, this one here, our average density. That's the first one's nothing, but the second one here is probably better. Copy. There, and yeah, someone asked me for this spreadsheet, and I look, I don't know everything about everything, and I often make mistakes. But what I do know is 100% is that if you teach someone how to do something, it's a lot better. I'm going to undo that because that didn't work. It's a lot better if you teach someone something rather than just give things away to people, because yeah, I mean, you want to learn, right? You want to learn, and this one here is pretty easy. This is that number there, remember? So we are going to, let's copy this up here, just so we don't lose that. Copy that, and we're going to put that escape under here. So I'm going to put that there, rightio. So what do I want to do here? I want to I'm going to color all these cells, right, that are different. Yeah. What am I going to use? I'm just going to drag this out a little. Here you go. There's some cells there. So I'm going to say these are explanatory, right? I'm going to call that explanatory. This one's explanatory. This one, all these actually, are explanations. Okay. You can still see that. And here we're going to do, here, this is a manual input. So this is just an input. And this one is a well, these are a manual input actually up here. Input, input, and input. These are all inputs. Input radio, and then this is also an input. It's just a 0. So I'm sort of coloring it with what it is, and these are calculations. Right, and this is also a calculation. Okay. This one's a calculation. This one is a linked cell. And these are calculations. And this one is a calculation. So you can see here that my explanation of them is up there, and these are we'll call these up here notes. These are neutral. This one is a calculation, which is down here, and this one is just a value. And this is this value. So I call it a neutral. Radio, there you go, neutral, there you go. And these will be titles, so we don't really need to worry about those. Make them look pretty. What a exciting time. And maybe since everything's in that other font, we will grab all those and change them to Rockwell font. There you go, Rockwell. So it all looks the same. Yeah, this is nice and pretty now. So we built this spreadsheet to tell you what our... And now you can go and play with whatever you like. So this is a cumulative kilogram. So if you really wanted to, you can do something special like format these cells. Sorry, I will squish this down a little. There it is, the edge. So you know, here we have this thing here, right? Our equations. We'll make that a little bit smaller. That's everything. Okay, I don't know if you feel comfortable. I will, you know, ask questions in the comments. Look, I don't know everything about everything, and if anyone says they know everything, or even say they're telling the truth all the time, then you take a second guess at what they're saying. But here we can also, just as a interest, I can format these cells, and okay, get these format cells up. Get these format these cells. We can add a little custom format in here. Yeah, and I'm going to just put in a equals kg. Pretty easy. There you go. All right. Right, now they're in kilograms. Yeah, pretty easy. All right. I hope that you hope that you have fun with this. It's pretty boring stuff, and I did a lot of drinking water and having sips from my tickly throat. And this is a bit longer than usual, and I just wanted to make sure that everybody was that the people that asked me about product densities and calculating these sorts of things get some value out of it. Hit me up in the comments of the video. Happy to talk about what I do know, and if I don't know it, I'll tell you I don't know it. Now if anyone else has any inputs and wants to suggest that this is not the appropriate way, I would love to hear from it, because this way I've been shown since 2012. No, earlier than that, 2005. I've been using this equation, so and it's been pretty reliable. So I would love to know if you think that I've done it wrong and that you've got a better way of doing it. But and I implore people to go and check out various equations like PVNRT, P1V1 equals P2V2. This is essentially this equation here is essentially P1V1 equals P2V2. You notice there's no temperature included in this, so temperature also has an effect, but we're just looking at the density compression. We can't account for everything, so I hope this helps you, and I hope you're able to build a spreadsheet from it. Yeah, well, I'm going to save this because I don't want to forget that I fixed the other bit, and I will see you all later. And I hope that my work has helped you out.